what's y'all's volume that y'all are resuspending?
They're pellets right now from a 100 mm dish.
Okay.
So it's like 1 to 2 million cells.
1 to 2 million. Okay. Well, I use about 10 million per pret, and that gives me 4 chromatin precipitations, and usually some left over to check the DNA shearing.
Right.
So, did I give you the protocol on how to check the DNA shearing?
You could give it to me again.
So usually I end up with about 500 microliters of resuspended chromatin. So when I do my chromatin preparations, I actually lyse the cells in a non-ionic detergent before I lyse the nuclei in a 1% SDS detergent. So then I dilute my chromatin 1 to 100 to get the SDS concentration below 0.1. Well, actually it's below 0.01, around 0.01. So then usually you end up with like whatever, your chromatin. And then for me, I use a setting of 8. And what type of cells are you using?
These are 8 human lung fibroblasts.
8549s?
Yeah, well, HFLs.
Okay. So ultimately it'll all depend on your cell type. So you just have to do a series of like assays basically. But usually I'll take one chromatin preparation and I'll sonicate it through a series of cycles, and I'll take out an aliquot every couple of cycles. And I usually start on cycle 4 to 8. I'll take 50 microliters out and assay in one big decross-linking experiment to check the chromatin fragments. But usually you need to have an ice bath, so this would be sitting in an ice bath. And you'll just basically set it underneath here and you'll hold it. And it doesn't have to be in the ice bath. But then what I like to do is just take this and I just... So I'll do that 3 to 5 times depending on the cell type, and then I'll set it in the ice. And I'll leave it there for 2 minutes on ice. So that would be right there, that would be 1 cycle. Okay.
So 3 bursts?
3 to 5.
Okay.
I like to do 5, but...
Alright, so 5 bursts and then 2 minutes on ice, and that's 1 cycle.
That's 1 cycle. And for MEFs, 8 cycles works great. For HFs, 6 cycles works great. And then I have a couple other cell lines I haven't determined yet. But the key thing is like, you don't want this to hit the wall too much. You want it as close to the bottom without touching the bottom, and you just want to do that. The biggest thing that you can like have a problem with is if you do something like this, where it's not towards the bottom, and then see how it sprays it out like that. You don't want that. Or if you leave it too long, you can foam it up like that, and then your chromatin's no longer usable if something like that happens. And then if you have infected versus uninfected, I always do the infected or uninfected first, and then I'll just wipe off the probe, and then I always wash it with a ton of just double distilled water. So at the end of that, basically you'll start it with a cloudy solution of what looks like this stuff, and then at the end of your sonication series, you'll know that your sonicated material is good to go because it'll clarify substantially. After you do your sonication, what you want to do is there's a lot of insoluble junk in there, and you want to spin that out by taking your tube and putting it in the 4-degree microfuge and at a setting of 14,000 times G for 10 minutes. And you'll see that there'll be this small little insoluble pellet, and that pellet shouldn't be bigger than 10% of the original starting volume. That tells you that you're sonicated, at least you sheared it okay. So then I can tell you the way that I check my chromatin shear. And I'll write this down. Let me get one of the solutions so I remember what it is. I'll just write this on this board.
Okay.
So you'll take anywhere from 50 to 100 microliters of chromatin, and then you'll bring it up to 200 microliters and 0.22 molar tris Cl, pH 6.8. SDS. So usually I do 100 microliters, and then I'll add. Sorry, I should actually say. So let's just say you took 100 microliters of your chromatin, which is usually a good number to start with. You'll want to add 170 microliters of this solution, and then 30 microliters of beta-mercaptoethanol. And then you'll heat that at 99 degrees for 1 hour in a heating block. And make sure that you have the things that hold the caps down. Okay? So after you heat it for 1 hour in this heating block, you'll let your sample cool. You'll kind of like collect the droplets that accumulated on the cap just by a light centrifugation, and then you'll add usually about anywhere from 10 to 20 micrograms of proteinase K. Okay. And then you'll heat that at 58 degrees for 1 hour in the heating block. Do you have a heating block, Randy?
Yeah.
Okay, great. So then, after you do that, your solution will be around 300 microliters. So you'll want to add in 300 microliters of 1:1 phenol chloroform. I don't even know how to spell that. Yeah. And make sure that's DNA chloroform. So then you extract. Everybody knows how to do a phenol chloroform extraction?
Yeah.
Okay. So then you'll extract and you'll take out 250 microliters of the aqueous phase. And you'll add 10 micrograms of glycogen, 25 microliters of sodium acetate. I don't know what the molarity is on that, but it's whatever you normally do for DNA precipitations. And then it'll be 625 microliters of ice cold ethanol, 100% ethanol. And then after that, you'll just precipitate DNA, and you'll do that by spinning at max speed in the 4 degree for anywhere from 30 minutes to 45 minutes. You don't have to go 30 to 45 minutes, it's just you get more DNA the longer you do it. And then you'll wash with the pellet with 70% ethanol. And then you'll resuspend it in, I think TE will work just fine. Or you can do Tris. Actually, this is what I do. Tris pH 8. Okay. Then what you'll need to do after that is to add, 10 micrograms of RNase A. And you'll let that go for 30 minutes at 37 degrees. And then you just want to add that mixture directly to your DNA gel and run it next to a ladder. And for good shearing, you should see a range, kind of a smear. I don't know if you've done it yet, but you should see a range between 200 and 1,000 base pairs, with the majority of it sitting around in between 300 and 500. That's when you're good. So ideally, we all have written this down. Ideally, when you do this, let's just say you have your cycle 4 here, 6, 8, 10. Ideally, like if this is 1 kb and this is 200 base pair, you should see it start a smear that starts about here and it might even be above 1 kb, and it'll slowly move down, and it'll tighten up as it moves down. So in this sort of situation, if this were 200 base pairs and the majority of it was 200 base pairs, you're a single nucleosome, and that's not very good for immunoprecipitations because you lose the robustness of the assay by doing that. So like you'd ideally want something in here. This would be a little bit too high, and if you see anything above that, that's way too high. What else should I say? And then if you see anything down below 200 like this, that's RNA. That means you either forgot to RNase treat or you didn't RNase treat enough. So usually, if you resuspend, for example, your final DNA pellet in about 60 microliters, usually I'll do like 10 microliters and 30 microliters because you don't want to have too much DNA loaded on the gel, or it'll run at a higher weight than apparent weight than it actually is. So I usually do like 10 and 30, and then compare between the two to make sure you don't overload or underload. Yeah, so I can show you what a gel actually looks like. So this is an example of DNA that isn't sheared gray. It's kind of what you're looking for. This is what it'll look like.
Let's see.
So this was just one experiment where I was optimizing for the human foreskin fibroblasts. You can see that with this set, there's a portion of the DNA above 1,000 base pairs, so ideally you'd want to eliminate that down to here. But that's what it's going to look like on the final gel.
So which one would you take here?
I mean, like, I'd say that the tighter it is, such as this one or that one, see how you can see that this one has it around 100 to 1,000 to 200, but see how it's darker within this region? Around 500. That's ideally what you want.
Okay.
And a lot of times, like, it's not that this is bad, like, this is usable. You just have to understand that, like, sometimes when you don't shear your DNA enough, your negative control regions will actually be a little bit higher than you might expect. For example, if you did an experiment one day and the chromatin looked like this and your negative control looked negative, very negative, and then all of a sudden the next day your chromatin looked like this, it might fluctuate. So, and that's why you need to not just have an IgG control, but you have to actually have a control for a region of the genome that you don't think binds insulators. Cohesin is going to be a little bit difficult, but you see what I'm saying?
Okay.
Yeah, so good luck with that, and then